Thinking Aloud. Conversations on the leading edge of knowledge and discovery with psychologist Jeffrey Mishlove.
Hello and welcome. I'm Jeffrey Mishlove. Today, we'll be looking at the transactional interpretation of quantum physics. With me is Dr. Ruth Kastner, who is a member of the Theoretical Physics Group at the University of Maryland, College Park. She is the author of The Transactional Interpretation of Quantum Physics, The Reality of Possibility. Her other books include Understanding Our Unseen Universe and also Adventures in Quantumland. Welcome, Ruth.
Thanks very much. It's great to be here.
It's a pleasure to be with you. My understanding is that the transactional interpretation, which is your specialty, was developed by a physicist named John Cramer at the University of Washington.
That's correct. Yes, John Cramer in the 1980s.
Mm-hmm.
Yes.
Why did he see a need to develop yet another interpretation of quantum physics?
Well, as I understand it, it was a little bit serendipitous. Professor Kramer was he's an experimentalist, an experimental physicist, and he had been looking into the Wheeler-Feynman absorber theory of radiation. It's a different theory of the way radiation works, the electromagnetic interaction. It's a different theory of how this works. And he was looking into this, and he suddenly had a sort of epiphany where he realized that this relationship between the emitters and the absorbers of what was then a classical theory of electromagnetics could be applied to quantum theory to explain certain problems in measurement, in understanding measurement in quantum theory. So he actually almost stumbled on it, but was inspired to pursue what he saw as a kind of a relational, transactional way of understanding measurement in quantum theory.
I suppose it's fair to say, and I know we covered this in an interview we did some years ago about interpretations of quantum mechanics, that almost from the very beginning, with Einstein and Bohr, there were controversies about quantum theory.
Right, definitely. And so he was one of those who wasn't satisfied with the way things were, and he developed an approach that actually seemed to explain where the quantum probability rule comes from, the so-called Born rule for calculating quantum probabilities.
Mm-hmm. So. Well, there's so much that we need to define for the benefit of our viewers. So let's start with the Born rule. That's pretty crucial to quantum physics.
Right. So in quantum theory, you have these things called wave functions, which in themselves were ideas that were proposed by Erwin Schrodinger. And he had his own approach to quantum theory. In general, they're really quantum states. They're kind of mathematical labels that we give to quantum systems to describe them and to be able to try to understand them and predict their behavior. So this thing that's called the wave function is really a kind of a quantum state that describes something like an electron or a hydrogen atom or something like that. And when you wanted to, back in the early days of quantum theory, when you wanted to try to predict what's the likelihood or probability that you're going to find your system in a particular state later or at a particular detector in an experiment, it turned out that you couldn't just look at this quantum state or wave function and the size of it, that what's called the amplitude. You had to actually square it. You had to take this wave function, which was a complex number, and take its complex conjugate and multiply them together and get a number that then made sense as a probability. So it was Max Born who realized, at one point in 1931 in a footnote in a paper he wrote that, it's not the size of the wave function. I have to square it. You must square it to get the probability. So it was kind of a mysterious rule that was named after Max Born, and it worked.
Mm-hmm.
But it seemed a bit ad hoc. It seemed as though people didn't understand where it came from.
And the irony is, I suppose, it works perfectly, I understand.
Yeah, it works very well.
Mm-hmm.
It works very well. So it's kind of like a mathematical recipe that was arrived at by an educated guess. And then, there are other reasons that John Cramer wanted to pursue his idea, but what appealed to him, I think, immediately, and also to me when I was learning about it, was that this mysterious Born rule just kind of came out of the dynamics of this picture.
Well, normally when we think of transmitters and absorbers, our normal metaphor, I think, for that is like radio. You have a radio transmitter and a radio receiver and a signal that goes from the transmitter to the receiver. But I gather that Kramers' vision of this is different.
Yes, it is. It's very different in that it's not unilateral. So the picture you just described is a kind of a unilateral theory of radiation that is very, kind of a common sense sort of intuitive picture that we see in our everyday world. But at the quantum level, this other theory has somewhat of a counterintuitive nature to it in that it's much more symmetrical. So it's much more on even footing in a way of things that we call emitters and things that we call absorbers. Mm-hmm. And it's much more, I kind of think of the yin-yang, the Eastern yin-yang picture, in that the picture you described was much more yang. It's sort of, it's sort of like the baseball picture of radiation, I like to think of it. It's just sort of one person does something, sends something out there, and there it goes. But in this absorber theory or direct action theory, it really kind of takes both entities to participate actively so that they're negotiating, and that ultimately what comes out of that is this transfer of whatever you might have energy or other quantities from the emitter to the absorber.
Well, in a way, maybe baseball is a good metaphor for that because, at least from my limited experience, if I'm at bat, I'm watching the pitcher as he's winding up, and I'm starting to swing almost as soon as the ball has left his hand because it's so fast. And so they're both kind of, the pitch is coming and I'm swinging at the same time.
Exactly. And that's, I guess we might be mixing metaphors a bit, but what you described pictures the batter as kind of the absorber, the one who's going to actively participate in what that ball is going to do. When I use the term the baseball picture, I'm thinking more of it's really a different metaphor, as if you had, say, a T-ball, and it just took one person to just decide, I'm going to hit that ball, it's going to go out there, and nobody needs to catch it or anything for it to have a trajectory and so on. So it's in that picture that I'm kind of using the term baseball.
So you're suggesting, or you and Kramer, since you were the two advocates now, and Kramer, if he's still alive, he's undoubtedly retired.
Right, but he's still very active. He's officially retired, but he's still doing things, and he's
so
still.
That would make you perhaps the primary exponent of the transactional.
At this point, probably, yes. Yes.
And I know you've updated the theory a bit since the initial presentation by Kramer.
Yes. What I've done is, I guess there are two main aspects to what I've done with the interpretation. I've expanded it to the relativistic domain so that I've explored what's going on at a more subtle level, what makes something an emitter, what makes something an absorber. Because some people had objections in terms of, aren't you just helping yourself to the idea that something absorbs something, and that's just like, that's undefined, and it's so people weren't satisfied with that. So what I've done is develop that, and I've identified certain aspects of the absorber theory at the quantum level that kind of fills in those gaps and explains, this is how we get absorbers to do what they do, and so on. And the other thing I've done with the interpretation is explore the ontology of it, such that what I've suggested is that we need to depart from the usual picture that everything that happens, everything that's physically real is always in space and time. So I've I've looked at the transactional picture, and I've proposed that it really only makes full sense. It's really only consistent, and I think indeed all of quantum theory is really only consistent if we allow for possibilities, for physically real possibilities, which is really an idea of Heisenberg.
Well, and isn't the Schrodinger wave function itself, I've heard it expressed in much the same way, that these are probability waves. They don't exist in physical space. Some people say they exist in quantum space or subspace or something like that. Aren't you sort of getting at a similar idea?
Well, definitely, yes. I mean, and people have used that kind of language. What I've done is try to be a little more precise about it, and try to describe more clearly how systems and processes can transform from just being possibilities to become actualities, which are really more inhabitants of space and time.
So what you're saying is that the transformation from a possibility to an actuality is a physical process, but it doesn't really quite occur in physical space as we understand it. That is the normal three-dimensional space, one dimension of time,
exactly
4D.
Yes. So I mean, I'm talking physics, if you will, but I'm using an ontology that a lot of physicists may be uncomfortable with, in that I'm saying, well, I think what the theory points to is the idea that these microscopic systems that require quantum theory are not space-time objects, but yet they serve as precursors to space-time phenomena, so that it's the results of measurements and those kinds of things that are space-time phenomena, and those are the actualities.
Because classically, I think people would say if it's not in space-time, it's not physical.
Exactly. That's been kind of the usual assumption of most practicing physicists.
And the other point that you seem to be making is that the function of the absorber, like an atom that might absorb an electron, is just as important as the emitter, another atom that might eject an electron, for example, that they both play an equal role.
Exactly, right. And that's the key difference of this picture. It really denies the usual unilateral idea that you have something like a photon just emitted, and then it goes its merry way and may end up here or may end up there. In this picture, in a very precise way, no real photon is ever emitted without the active participation of absorbers. They must be part of the process in order to even get a real photon to exist at all.
And the intriguing thing here is that if we're looking at it from a cosmological perspective, if a photon is emitted in a distant, let's just say from the Andromeda galaxy, which is 1 million light years away, and it's absorbed by an atom that exists in somebody's retina, that from the point of view of a person on Earth, that photon took 1 million years to get here. But if I understand you correctly, the handshake, so to speak, between the absorber and the emitter takes place outside of space and time completely.
That's right. The processes that make that possible, that are part of the sort of behind the scenes negotiation that make it all possible, are going on in what I call Quantumland. That the space-time phenomenon is a phenomenon. It's an actuality, and these things are happening whether or not we happen to perceive them or not. You might have a plant or some other absorber that we don't know whether or not it's conscious, but it's participating in the sense of being an absorber.
And that participation does not involve movement.
Not in the space-time sense, no. Now, the other subtlety here, though, is that, people might say, well, that sounds really bizarre. How could my eye be having anything to do with this photon that's coming from so long ago? But in fact, the sort of Quantumland picture where these particles and particle pieces of mass that are the absorbers and emitters can change too. So in other words, what is in the Quantumland behind the scenes realm can change as well. So that's always changing. It's just not changing in a way that's tagged to a time index in the sense of space and time.
In other words, there is action of some sort, but not what we would normally think of as movement through space and time.
Right. It's not motion in the sense of, that would be described, say, by relativity theory.
Yeah. Now, there's a strong tradition in Western philosophy, positivism. It still, I think, carries a lot of weight in many circles, not particularly with me, and I suspect not with you either.
No.
but the idea of logical positivism is that if you can't measure it, it doesn't exist. There's no point even in talking about it.
Right. And I mean, that whole program kind of blew itself out quite a few decades ago. It was an understandable attempt to be rigorous and, to be empirically disciplined and not go off on wild flights of fancy, which of course is admirable. But it's really kind of self-defeating. And I think I read somewhere not so long ago the idea of someone said, how can you verify verificationism? Well, you can't.
Right.
I mean, so it's not even, it can't even conform to its own standards.
But no theory conforms to its own standards.
Well, right. And of course, a theory of knowledge always ends up being restrictive. Because when you try to say, well, the only way you can legitimately gain knowledge is by following, these rules that I'm going to lay down, inevitably you're going to probably break your own rules. And other people are going to come up with knowledge that by your own ideas shouldn't have been possible, but turns out to be well corroborated.
Yeah. When I was a graduate student at Berkeley, I got to know Paul Feyerabend, who was a well-known philosopher of science who was a strong critic of the positivist approach. He used to I think he wrote a book called Science in a Free Society, and he put his astrology chart on the back cover.
Yes.
And his
he was a rebel.
He was a rebel, but his point was that some of the best, most significant advances in science occur when people break the normal rules.
Of course. And of course, the great example of that is Ludwig Boltzmann, who broke a whole bunch of rules, empiricist rules, when he started imagining atoms and saying, hey, what if there's this in his time, in principle, unobservable object that if it's behaving a certain way, if I can describe it a certain way, and the way he described it was also kind of innovative in terms of statistical ideas, then maybe I can explain what we observe in the phenomena that we observe. And it turned out he could, and it was a very powerful theory. And of course, the people at the time were dead set against what he was doing because, you couldn't verify the existence of atoms, and it was metaphysics and hand waving and so on. But he turned out to be right. Now,
Boltzmann, to my recollection, is most remembered for his theory of entropy.
Right. These thermodynamical laws that were kind of macroscopic laws that were very well known at the time, but also were kind of empirically based. In other words, they were just patterns and regularities that were observed, and they weren't really explained well in terms of why do we have these phenomena. And Boltzmann's idea of atoms and their behavior really broke new ground in explaining those things.
I seem to recall that his equation for entropy is actually engraved on his tombstone.
That's what I've heard. Yes, yes.
Anyway, we're getting, I want to come back to the transactional interpretation because it has a number of unique features to my understanding. And one of them, correct me if I'm wrong, is that the classical Copenhagen interpretation of quantum mechanics requires the observer to, as I think the term is the collapse of the wave packet. That when you go from Schrodinger's wave equation to an actual observation, that's known as the collapse, and consciousness must be involved because you don't see the collapse until you see it, until there's an observer.
Yes, well, actually, I think we've discussed this a little before, that the Copenhagen interpretation has so many different interpretations, definitions that some people would say that it actually doesn't have collapse. Yeah. I think the people who were had most affinity for the collapse idea were von Neumann, and then were some people who would perhaps call themselves Copenhaganists who also would say, as you put it, that it's the observer that somehow brings about a collapse.
Von Neumann and Wigner, as I recall.
Yeah, I think Wigner said that too. And that they kind of did that because they really had no other way of explaining why is it that we see determinate phenomena? Why is it that we see, the metaphorical Schrodinger's cat either alive or dead? Some people like to say awake or asleep because they don't want to, they're cat lovers. Yeah. But we see one or the other, and the strict application of quantum theory in its usual understanding is what's called unitary only. It's only deterministic. And the law that supposedly predominates in quantum theory as it's usually understood only allows these superpositions and these correlations, and it doesn't allow anything to collapse. It doesn't say why anything collapses or why you get anything but a steadily increasing superposition. But that conflicts with our everyday experience. Yeah. So that's why they said, well, I guess it's consciousness. I can't see any other, if I keep describing things by quantum states, they keep getting more and more superposed. At no point do I see in my math what I'm experiencing in the world. So there was this kind of gap in the explanation that they filled in by saying consciousness collapses the wave function.
Now, the transactional interpretation doesn't go that way.
That's right. It doesn't do that because if you include this more symmetrical two-way understanding of the way fields work and the way they interact, then it's actually the systems that are interacting that indeterministically at some point will lead to what's called a non-unitary process where there is collapse or reduction, as some people call it, where there will be actualization of one of these possible outcomes. And of course, that's not to deny consciousness. For all we know, these systems could have some innate consciousness. If you believe in panpsychism, then on some level there's consciousness, perhaps in different levels of complexity or awareness at different levels. So that's not to deny consciousness, but it's good just to give a more complete understanding of why we have the experiences we do.
You've pointed out that to include consciousness in a quantum explanation is problematic because consciousness is undefined in quantum physics.
That's part of the problem. Of course, when you have these scenarios like Wigner's friend, which was one of the versions of the Schrodinger's cat experiment, where instead of the cat, you've got a friend of Wigner doing some experiment, and then Wigner outside the lab, and according to standard quantum mechanics, Wigner has to describe his whole friend and his whole lab by this giant superposition that he will never see. And so, but his friend was conscious, wasn't he? So why wouldn't it collapse then? And there's just, you never know at what point do we bring in consciousness? At what point does something really collapse?
Now, for purposes of clarification, I think it's fair to say that even though you acknowledge that quantum physics has no definition of consciousness, you are open to the possibility of metaphysical idealism, for example, that everything is consciousness.
Okay, yeah, that's an absolute possibility, and that's certainly consistent with it's in no way conflicts with, the model I'm proposing. It's it becomes a separate question in a way. I mean, the model that I'm proposing does open the door for, the idea that things can be physically real, but they aren't empirical. Yeah. Okay. And then once you allow for that, then you can also allow for the idea that mental realities may have their own existence, and we can't go around saying, just because we can't measure it, or we can't measure subjective experience, therefore it's not real or it shouldn't be talked about. So I see this as an exploration that can help to expand our ontological categories.
William James was a psychologist. At the end of his life, proposed what he called radical empiricism, and I think by that he meant that our subjective experience is the most direct form of empirical knowledge.
Yes, I mean, in a way, it's firsthand. It's undeniable. I guess what the typical physicist response to that would be, well, it's not empirical in the sense that it's not third party corroborated. Mm-hmm. And I think some people use the term empirical to mean, data or information that has to be multiply corroborated. For instance, we can all corroborate the existence of these flowers, and we can all agree there are flowers there. But each of our perceptions of what these colors are is something that we can't really, that's our own private subjective reality. But again, as you say, it's firsthand and it's very real, and nobody can tell me I'm not seeing pink here.
Well, I know this is a bit of a digression, but it does seem to me that we are getting some corroboration of subjective experiences when you get, for example, multiple reports from people who've had the near-death experience, which is very subjective, very internal, but we now have thousands of reports from people, and there are many consistencies.
Right. And those kinds of data are, they have patterns that are undeniable, and it certainly is data. I mean, again, when you ask a physicist, I'm trying to kind of put myself in the mindset of the critical physicist. Yeah. They might object by saying, well, again, these were first-person accounts, so in that sense, they would probably say they're anecdotal. Yeah. That the physicist might say, well, I couldn't read a dial. I couldn't go into the lab and read a dial and corroborate that person experienced that. So that's where that's where their skepticism comes in. But certainly when different people from all walks of life and different belief systems are reporting experiences that have these commonalities that otherwise wouldn't be predicted, then that's certainly noteworthy.
Yeah. So back to the transactional interpretation. One of the ideas that you also get into is in your version, which you call relativistic. The relativistic transactional interpretation is the idea of determinism and the block universe.
Well, yeah, my picture denies that. Yeah. So, I think a lot of interpretations these days, and not mine again, but a lot of people want to try to understand quantum theory by putting in hidden variables and sort of additional content that helps them to regain a sense of concreteness that otherwise you don't really tend to get with quantum theory. And a lot of these folks end up with a theory or a model that implies that all events exist as space-time events from the beginning of time to the end of time. Yeah. And that's kind of a block world. That's what that means.
Yeah, everything is sort of frozen if you can see all of time at once.
Right. And so a lot of people kind of use the term God's eye view, which is very tendentious because it presumes that you have a block world and God's looking at it, which we don't know. Maybe God is if you take my picture with the iceberg and the submerged portion, maybe God's hanging out in the ocean somewhere watching things grow. Who knows what God is seeing? But yes, that picture is it's a static picture. And the problem with it is a lot of the discussion about it and in the presentations of these models use dynamical language and dynamical storytelling and zigzags and things going back and forth. But in fact, they've got a static block of events, and that is their ontology.
And that is, if I understand you correctly, that's based on Einstein's deterministic theory of relativity.
Well, some people would say that it's an implication of his theory, but that's actually highly debatable. And there's one author, if I can remember his name, Milik Kapek, I think, who has argued that it's actually a distortion of relativity to say that it implies a block world. It's certainly one interpretation you can make of relativity.
Einstein never put it that way, I guess.
I think informally Einstein may have expressed preferences for this idea because he also kind of rejected the indeterminacy of quantum theory. So he was one of those who really wanted things to be more concrete. And that was clearly kind of his metaphysical preference.
So are you suggesting then that if we accept a strictly determined universe, then the idea of the block universe is implied?
I think so. I mean,
necessarily implied?
If you have a model in which there are laws or constraints that determine for all times, all spaces, all places, and all times what should happen, then you do have a static ontology.
In effect, if I knew the position and momentum of every particle in the universe, I should be able to calculate from that everything back to the beginning of time and everything forward to the end of time.
If you have deterministic laws, yes.
Yeah.
Yes.
But your transactional model is not a deterministic model.
That's correct.
Nor is quantum physics in general.
That's correct, yes. So I take that seriously, and what I say is that we actually, of course, we do have a space-time manifold, if you will, but it's something that is growing. It's something that is not static.
Yeah.
So that the future is really just possibilities.
Well, if I recall correctly, and from some of my previous interviews, because I'm not a scholar of physics like you are or other guests are, but I'm told that Einstein himself said that space and time are not primary. They are not the matrix in which we live, but they are created by by matter and energy, by the movement of matter and energy.
Yes, he did say that toward the end of his life. Yes, so he didn't. I think he went through an evolution in his thought, but toward the end of his life, he did say things to the effect that there's no space-time apart from the events that make it up, and that's very much similar to my picture that the events that come out of the transactional process are the space-time manifold, and it changes
because we normally think of space as being the matrix in which we move about.
Yes.
I mean, that's just common sense. I'm sure everybody thinks of that, and time is also a matrix that we go through from birth to death.
That's the way it seems. You know, it definitely feels like we have a container of space and time that contains everything. But, you know, we have to be careful of these impressions that seem so obvious to us.
Incredibly seductive.
It is. And it's so seductive that we don't even know that it's not necessarily true, that it's optional to think that. And it's very much similar to the way, you know, in medieval and early Renaissance times, people thought that they saw the sun going around the earth. Because that's what they saw. Yeah. And so it's obvious that the sun goes around the earth. But it's wrong. You know, we found out later that's wrong.
So there are probably other things like that, but we're getting very close to the bottom of how many things could be wrong if space and time are what we think they are, what's left.
Right. And that's the challenge of quantum theory, that it was a big surprise to the scientists who came up with it. They weren't looking for it. You know, at the end of the 19th century, they thought they had everything just about explained, and there were just these two little clouds on the horizon that did black body radiation and the spectra of atoms that were discrete that they couldn't quite explain, and then they had to redo everything.
Now, today in physics, I know that there are groups of physicists working on different theories. I understand, for example, there might be 1,000 physicists today working on string theory and variations of string theory. How is the transactional interpretation doing in the world of academic physics?
Well, it's still kind of the odd guy on the block, so to speak. It's the challenge it faces is that it's based on this theory, the direct action theory of fields, that kind of has a bit of a stigma attached to it. And part of that is because the people who developed it, John Wheeler and Richard Feynman, they developed it for certain reasons, and they kind of turned away from it because it didn't serve the purpose for which they were originally investigating it. But there are a lot of misconceptions about it. It also has a kind of non-locality, which people are uncomfortable with. And it has this sort of backward in time, which in my picture isn't a literal backward in time process, but there has that sort of reverse temporal character that is also viewed as not physical. So there are reasons that people are not comfortable with it, although it turns out that later in life, Wheeler did come back to it, and he started trying to promote that as a way forward, and people aren't really aware of that. But it's just very counterintuitive, and you know, people are not quick to warm up to it.
The direct action theory of fields.
Right. And that's also the absorber theory of fields. So it is a non-local theory. So it has that kind of, people like to think of propagation as kind of a bucket brigade where things go from one point to another in a very local way. And this theory doesn't work that way.
Now you used the iceberg metaphor a moment ago, and I gather by that you mean that at the tip of the iceberg, the small part that is visible to us, that's what we would think of as events in space-time, but underneath a much larger portion of the iceberg, in the case of an iceberg, 7/8, but perhaps in your model it could be even much larger, is outside of space and time completely.
Right.
But very essential, very important, so that an emitter, an absorber of a photon or an electron has all of this other invisible activity going on.
Right. It's all behind the scenes. And, and that's why it has this strange counterintuitive behavior, the non-locality and the superpositions and the kind of indeterminacy that is so startling and so puzzling. And of course, a lot of physicists responded to that by just saying, well, it's not real. It just can't be real. It's too weird, I mean, Bohr himself said there is no quantum world because to him, those kinds of behaviors did not satisfy his criteria for what should be regarded as physically real. So he just said it's not real.
And if you define reality as something that you can touch and measure, you'd have to come to that same conclusion.
Right. And that's what he did. But I mean, that led to inconsistencies. He would say things like, quantum systems in themselves are abstractions that have no properties apart from their interactions with a physical system upon which they become, I forget what the quote is, but upon which they gain properties. But that makes no sense because if it's not real and if it's not physical, how does it undergo physical interactions? So he would say these things that really, were inconsistent and made no sense.
So what you're saying is that this stuff that's taking place outside of space and time is essential. We wouldn't have a physical world without it.
Absolutely. It is the bulk of our physical world. Yes.
And if we were to apply that same interpretation to ourselves as human beings, it would suggest that 9/10 or more of who we are is invisible.
Who knows how much who knows how small that tip is in comparison.
Right.
I mean, I was having a conversation recently with someone who's from India who is also looking at quantum physics, and he didn't like the idea that I was saying that the bottom of the iceberg, the hidden portion of the iceberg of quantum theory is the, hidden reality, say, of the Indian tradition of the Brahman and so on. And because it's too small. Brahman is huge and so who knows how big it is.
It could be, trillions of times.
Yes, of course. We don't know.
Yeah. And in fact, it's immeasurable in any case.
That's correct.
So one might say that this we'll call it the quantum reality or Quantumland, I think is your phrase.
Yes.
It's immeasurably larger than what we think of as physical.
Right. Because there's no boundary on it in the sense that, if you believe there are quantum fields or these are even more subtle than what I draw, as the submerged portion of the iceberg. This is sort of the water. And metaphorically speaking, there's stuff going on in the water that can become part of this more solid iceberg, but it's still not manifest as phenomena. So there are all levels, I think, of the sort of behind the scenes activity.
And I gather that it's hard to describe it except using metaphor.
Well, exactly. And of course, what I always say is, the quantum theory is describing it. People say, you should be quiet because you can't use words, the limitations of language. You can't talk about it. Well, yes, we can. The theory is a kind of language, and it has a structure.
You mean like the Schrodinger equations.
And Hilbert space. These are these mathematical structures that are part of the theory that Heisenberg also came up with a mathematical structure that appears in different ways depending on which version of quantum theory you're looking at. But they're all isomorphic, meaning they have the same basic form. And this form is in itself a language that can be referring to the structure of these unseen quantities. So when people say, well, you're not allowed, you can't use classical language to talk about it, therefore be quiet and you shouldn't say anything about it. But in fact, the theory is saying something about it. There are possibilities. They have a Hilbert space structure.
A Hilbert space is a space, I understand, of infinitely many dimensions.
Well, depending on which system you're talking about, it has to do with degrees of freedom of a particular system, and that will dictate the dimensionality of your Hilbert space. Yeah. So even a given Hilbert space doesn't describe all of quantum theory, but quantum theory tells us that for whatever systems are of interest, they themselves have this Hilbert space structure.
So, and if we look at the mathematics underlying quantum theory, and I know there's a vast array of mathematics that is now being brought to bear, catastrophe theory and gauge theory, and it goes on and on and on. Those are very precise descriptions.
Yes.
Of this quantum reality.
Yes. So it is very quantifiable in the sense that it has a structure.
Yeah.
So my point is, well, we do have a description. We do have this apparatus that works so well. And we can either say, okay, well, it's just a recipe book or an instruction manual for our experiences, but that's just kind of to duck the whole question of why does it work so well? And why can't you, think that it has something to tell us about reality, even though we can't say, well, it's located at this position and it has this color and this size. Well, we don't need to use that kind of language because we know that only applies to the tip of the iceberg.
So in that sense, it would seem to me you are a Pythagorean.
Well,
by which I mean that the mathematics is what, in effect, underlies all of reality.
We've kind of been forced to deal with this theory that forces us to consider the idea that what we see of reality isn't the whole story because something else is going on and it has this mathematical structure. So maybe that is the structure of reality, even if we can't see it. And I guess where we might differ is that I don't go into numerology in the sense that I don't think every single number and every single mathematical concept necessarily describes something about physical reality. But clearly quantum theory kind of forces itself on us that it works and other theories don't.
Yeah. Well, Ruth Kastner, this has been a very enlightening conversation. I'm delighted that you're here with me in Albuquerque, and I plan to have a few more with you while you're here. We're getting into some of the real paradoxes associated with quantum theory, and let's see how they look in the light of the transactional interpretation.
Very good. I'm looking forward to it.
Thank you, Ruth, and thank you for being with me, and thank you for being with us.